So we're still on chapter 15, functions of several variables. And let me just review something about directional derivatives. And what is called the gradient of a function of 2 or 3 variables. So what's a nice example to start with? So we have always some function z of x and y. So f is a function of 2 variables. And if we think of the domain of this function as being the xy plane, then for every point xy in the plane, you have some number f of xy. And if we look at the point in 3-dimensional space, whose height is that f of xy, the set of all those points is some surface, which we think of as the graph of a function. And we can talk about the rate of change of the function as x and y vary. And if you fix y, so you're only going to let x vary, the rate of change of the function is the partial of f with respect to x, or f sub x, same, different notations for the same thing. And if you fix y, if you fix x, and for fixed x, you change the function in the y direction, the rate of change is the partial of f with respect to y, or f sub y. But more generally, we want to know if you take some direction u, what is the rate of change in the direction u? And we let u be a unit vector. So this means a vector whose length is 1. And we want to find the directional derivative of f in the direction u. And we saw that this is exactly, if we let u have components, say u1 and u2, this is the partial of f with respect to x times u1 plus the partial of f with respect to y, u2. And we can think of that as a dot product. If we took the vector whose first coordinate was the partial of f with respect to x, and whose second coordinate was the partial of f with respect to y, and we take the dot product with the vector u1, u2, that's just a nice vector way to write this directional derivative. And this vector we call the gradient of f. And this is u. So the directional derivative of f in the direction u is the dot product of the gradient, where the gradient of f is this vector, or we can write it like this, or if we want to use I and j notation, this is the partial of f with respect to x, I, plus the partial of f with respect to y, j. Okay. So this is the fundamental formula for the directional derivative of a vector, of a function in 2 variables. And exactly the same rule holds if you have some function that, say, w is a function of x, y, and z. We take a unit vector u, where u has coordinates, let's say u1, u2, u3. The gradient of f is the partial of f with respect to xi, partial of f with respect to yj, partial of f with respect to z, k. And the directional derivative of f in the direction u, again, is the dot product of the gradient of f with u. Now, this tells us something very interesting, because if we take the absolute value of this vector, remember the dot product is the length of the vector f, gradient of f, times the length of the vector u, times the cosine of the angle between these two vectors. That is, if we have, here's the gradient of f, here's u, and theta is the angle between them. This is the definition, a definition of the dot product of two vectors. Is the product of the lengths of the vectors times the cosine of the angle between them. But this is a unit vector, that's equal to 1. So this is the absolute value of the gradient of f times the cosine of theta. And cosine of theta is between -1 and +1. This takes on its largest value when cosine theta is 1, which means theta equals 0. That means the angle between these two vectors is 0. That means u is in the direction of the gradient. So the direction of greatest increase of a function is in the direction of the gradient. This is smallest when cosine theta is -1. So the direction of smallest increase or greatest decrease is minus the gradient of f. So this tells you in what direction you have to move if you want the function to increase most rapidly or least rapidly. There's another very useful piece of information about a function that comes from the gradient. So suppose we have a function z equals f of x, y. So what is the level curve? The level curve, f of x, y equals some number c, is the set of all points x, y in the xy plane such that f of x, y equals c. So for example, if you have a function f of x, y equals 2x squared plus 18y squared, the level curve f of x, y equals, I don't know, let me make this 12. F of x, y equals 6. That's a level curve. That's all the points where 12x squared plus 18xy squared, 12x squared plus 18y squared equals 6. Or 2x squared plus 3y squared equals 1. And you should recognize this as an ellipse. When y is 0, x is plus or minus 1/√2. And when x is 0, y is plus or minus 1/√3. So the level curve for this function for the value 6 is this an ellipse. This is a level curve. This happens to be an ellipse. I mean, if you were to look at the surface this defines, it's some sort of elliptical paraboloid. And here in the plane, we have this level curve. And above that, these are all the points that are 6 units above the xy plane. So this is the curve, this is the surface, z equals f of x, y. Here we have a level curve. Now, suppose we have some function r of t moving in this level curve. So let's see. So what I want to say is, suppose r of t is some function x of t, y of t. So this gives us a curve in the xy plane. And let's say it's a curve on this level curve. So f of r of t is equal to 6 for all t. So df dt is 0 because this is just a constant function. But what is this? This is the derivative with respect to t of x of t, y of t. And by the chain rule, this is the partial of f with respect to x, dx dt, plus the partial of f with respect to y, dy dt. Df, partial of f with respect to x and partial of f with respect to y, that's the gradient of f. And dx dt, dy dt, that's the tangent vector to the curve. That's r prime of t, right? If r of t is x of ti plus y of tj, then r prime of t is just what you get by differentiating your two coordinates. Equals 0. So whenever you have a level curve, if you parameterize it by some function r, the tangent vector is always perpendicular to the gradient of the function. So the gradient of the function always points in a direction perpendicular to the tangent vector. So again, this is something you have to read carefully in the text. It's in section, it's in chapter 15. And the section on the directional derivative and the gradient. Now, what I want to talk a little bit more about today is tangent vector and tangent planes. So what can I say about that? Let's see. If someone's asking about what's being covered on the test, it's basically chapter 15, but of course, it's always the case in mathematics that whatever is the latest topic you're learning, studying, it usually requires that you know what came before. But all of the questions directly, I believe, are going to be like on the review sheet and come from chapter 15 up to the tangent plane.
Professor, will there be around like the same amount of problems, like 14 on the test, or will it be shorter?
Much shorter.
Much shorter? Okay.
Oh, yeah, sure. I mean, it's not a practice exam, it's just an example of the types of things you're supposed to know from what we've done so far in this chapter, up until the time of the exam.
All right. Thank you, Professor.
So, and the exam will cover not all of chapter 15, but up to section 15.6, This is on tangent planes. And this is just sort of a higher dimensional analog of what you learn in Calc 1. In Calc 1, you have a function y equals f of x. And at any point on the function, you might want to draw what we call the tangent line. It's a line passing through the curve at a certain point, which gives you, among other things, a linear approximation to the function. So this is a line that, say this is x equal a. So this point would be a comma f of a. So it's a line through this point on the curve. And the slope of the line, which is all you need to understand the line, a point on the line plus the slope, is the derivative of the function at a. And then the equation of this line, this tangent line, is y equals f prime of a, x minus a, plus f of a. So that's the line through the point a comma f of a on the curve, whose slope is the derivative. And this is a very good approximation to the function. So for x close to a, f of x is close to f prime of a, x minus a plus f of a. Right? This is a linear approximation to your curve. And we want to do the same thing in one higher dimension. So now our function is z, a function of x and y. So we have some surface, which is the graph of the function. And if you take a point AB in the plane, on the surface, you have the point AB, f of AB. And I want to be able to approximate this complicated function by something which is just a plane. Just as for a curve, we approximate a curve which is round and complicated by a straight line. Now, you have to know what is the equation of a plane, right? Remember, for a line, equation of a line. To know the equation of a line, you need to know one point on the line and its slope, the slope, df dx. How do you find the equation of a plane? Suppose you know a point ABC on the plane. What information do you need to be able to write down the equation of the plane? Interesting. If you haven't thought about this, how do you write down the equation of a plane? Let's look at an easy example. Suppose here's x, y, and z. Suppose you want a plane that hits the x-axis at A, the y-axis at B, and the z-axis at C. So here's the triangle connecting those 3 points, and we extend it. So what is the equation of that plane? So a plane always looks like AX plus BY plus CZ equals D. That's the general equation of a plane. And let's say we want the points A0, 0. This would be B0, 0, B0, and 0, 0, C. We want these points to lie on the plane. So that means when you plug in these coordinates, you get an equality. So for example, you plug in A0, 0, you get capital A, little a, plus 0 equals D. And you get, when you plug in this point, 0 plus capital B little b plus 0 equals D. And when you plug in this point, you get 0 plus 0 plus C times little c equals D. So what does that say? How can we solve for A, B, C, and D? So this says that capital A is D over little a. Capital B is D over little b. Capital C is D over little c. So if I plug this into this equation, I get D over AX plus D over BY plus D over CZ equals D. I can divide by D, I get 1 over A or X over A plus Y over B plus D plus Z over C equals 1. So that's the equation of the plane that intersects the X, Y, and Z axes at A, B, and C. And if we were to solve this equation for Z, we would have Z over C is 1 minus X over A minus Y over B, where Z is given by, multiplied by C minus C over AX minus C over B, Y. So if I have some function f of x, y equal to this, that gives me, that is the equation of the plane. And for this function, the partial of f with respect to x is minus C over A. The partial of f with respect to y is minus C over B. Yeah. Right. So again, if you haven't thought about graphing a plane, this is really something worth thinking about. But you might say, well, there's another way to describe a plane, and that's the following. So suppose I have a point in space, A, B, C, and I have some vector, let me call it U. I could look at all the points, all the vectors from A, B, C, which are perpendicular to U. So U would be a normal vector to the plane. If I know a vector U perpendicular to the plane and a point on the plane, I can write down the equation of the plane. Because if I take any vector x, y, z, the vector from ABC to x, y, z will be x minus ai plus y minus bj plus z minus ck. And I want that vector to be perpendicular to u, which means the dot product, let me call this u1, u2, u3, has to be 0. So the equation of my plane, when I take the dot product of these two, is u1 x minus a plus u2 y minus b plus u3 z minus c equals 0.
Excuse me, Professor, can you move the paper so
sorry.
you can see the top? Thank you.
Yeah. So what I'm saying is, if you take a vector, a point in the plane ABC, and a vector whose tail is at that point, say a vector u, we want to find the plane through this point with normal vector u, perpendicular to u. So point x, y, z lies in that plane if the vector from a, b, c to x, y, z is perpendicular to u. So this vector has coordinates x minus a, y minus b, and z minus c. And let's say u has coordinates u1, u2, u3. The dot product is this. It's this linear expression, something times x, something times y, something times z equals a constant. So that describes one of several ways to write down the equation of a plane. Now, what I want to say about the tangent plane to a surface is it's going to be the plane through a point where the normal vector is the gradient. So you could have z equals f of x, y. That's an explicit form of a function of z is a function of two variables. Or you could have some function capital F of x, y, z. And this is an implicit. If you look at all the points where capital F of x, y, z equals c, that gives you implicitly a surface in space, a surface in R3. Right? So for example, you could say, suppose you have the function z equals 1 minus x minus y. So here you have some function f of x, y. And you want to find the level surface z equals 0. So that's all the points where x plus y equals 1. Or we could look at a function capital F of x, y, z equal x plus y plus z. And we could ask for the surface where f of x, y, z equals 1. That's all the points where x plus y plus 1, x plus y plus z equals 1. Sorry, here I don't mean the level surface. I mean the, if z is 1 minus x minus y, the graph of this is a surface. Or if we look at x plus y plus z, the level surface z equal 1 is exactly the graph of this function. So if we take z equal 1 minus x minus y, the graph of this, the surface it defines, is the point line is 1 plus x plus y. Z equals 1 minus x minus y, so x plus y plus z equals 1. So this surface is exactly all the points that satisfy this equation. If you take the function capital F of x, y, z equal to x plus y plus z, this is the level surface, x capital F equals 1 or x plus y plus z equals 1. Well, the whole point of this is simply that you have two ways always to define a surface. You can define it explicitly as the graph of a function of two variables, or implicitly as the level surface of a function of three variables. And so suppose we have this implicit form, f of x, y, z equal, let's say 0. So we're looking at all the points, the level surface, all the points where f of x, y, z equals 0. That's a level surface in R3. And we want to find the tangent plane at some point P0 on the surface. So this surface looks like that, and here we have some point P0. And suppose in this surface, I have a curve R of t. So R of t, which has three coordinates, x of t, y of t, z of t, this is a curve in the level surface. So F evaluated at R of t, this is F evaluated at a point on the level surface, that's always equal to 0, it's constant. So if I take the derivative of F with respect to t, that's a constant function at 0. But this is the derivative with respect to t of F of x of t, y of t, z of t. And it can also compute the derivative. I will also compute the derivative by using the chain rule. So 0 is the partial of f with respect to x, dx dt, plus the partial of f with respect to y, dy dt, plus the partial of f with respect to z, dz dt. But this is exactly the dot product of the vector partial f with respect to x, partial f with respect to y, partial f with respect to z, with x prime, y prime, and z prime of t. This is the gradient of f. And this is the tangent vector r prime of t. So this says that if you take any curve in the tangent plane, here is its tangent vector, and that vector is always perpendicular to the gradient of f. So in the tangent, in the surface, at any point, the gradient is perpendicular to every tangent vector through this point, which means that every tangent vector is perpendicular to this. That what we want to call the tangent plane is exactly the plane through this point, perpendicular to the gradient. So tangent plane at P naught is the plane perpendicular. That's what this symbol means, perpendicular to the gradient of my function f. Which means the following. So here's my plane. This is f of x, y, z equals 0. Here's a point, P naught, with coordinates a, b, c. And the tangent plane at this point will be the plane perpendicular to the gradient. The gradient of f is partial of f with respect to x, partial of f with respect to y at this point, partial of f with respect to z at a, b, c. So the tangent plane will have the following equation. Partial of f with respect to x at a, b, c times x minus a plus partial of f with respect to y at a, b, c, y minus b plus partial of f with respect to z at a, b, c, z minus c equals 0. This only makes sense, of course, where the gradient of f is not the 0 vector. Some of its coordinates can be 0, but it can't all be 0. So here's a classical example. If you take an ellipsoid in space, so an ellipsoid might be something like x squared over 9 plus y squared over 25 plus z squared equals 1. So that's some ellipsoid. Or we would write this better like this. We have the function capital F of x, y, z equals x squared over 9 plus y squared over 25 plus z squared minus 1. And we're looking at the level surface where capital F of x, y, z equals 0. And we want to find the tangent plane at the point. Let's see, what's the point on this surface? If I take f at 0, 4, 3/5, what do I get? I get 0 squared over 9 plus 4 squared over 25 plus 3/5 squared plus 3/5 squared minus 1. That's 0 plus 16 over 25 plus 9 over 25 minus 1 is 0. So this point does lie on the surface. And here's the tangent plane for this function f. The partial of f with respect to x is 2x over 9. The partial of f with respect to y is 2y over 25. The partial of f with respect to z is 2z. When I evaluate these at the point 0, 4, 3/5, this is 2 times 0 is 0. F sub y, the partial of f with respect to y at that point, is 2 over 25 times y, which is 4, 8 over 25. The partial of f with respect to z at this point is 2 times the z coordinate, 2 times 3 over 5. So my tangent plane will have coordinates 0 times x minus 0, which is just 0, plus 8 over 25, x minus 4, plus 6 over 5, z minus 3/5 equals 0. Or this is the same as 8 times x minus 4 plus 30 times z minus 3/5 equals 0. 8x minus 32 plus 30z minus 18 equals 0. So 8x plus 30z equals 50, or 4x plus 15z equals 25. That's just arithmetic. So I don't want this to seem more complicated than it is. There really is a basic formula you need to remember that describes the tangent plane. Right? So the basic formula, if you have a surface given by f of x, y, z equals 0, the tangent plane at a point A, B, C on the surface is the plane whose equation is partial of f with respect to x at a, b, c times x minus a, plus the partial of f with respect to y at a, b, c, y minus b, plus the partial of f with respect to z at a, b, c, times z minus c equals 0. So let me just do a couple of problems to make it, I hope, a little bit clearer what we're doing. So I always like to pick problems in the book. So let me find some problems in the book at the end of this section. Here we have a function, or we have a level surface, if you like, x squared plus y cubed plus z to the fourth equals 2. And on this surface, we have the point 1, 0, 1. So on this surface, I want to find the tangent plane at this point. So let me think of this as the function f of x, y, z equals x squared plus y cubed plus z to the fourth minus 2. And we're looking at the surface, the level surface, where this is equal to 0 at this point, because 1 plus 0 plus 1 is 2. Partial of f with respect to x is 2x. Partial of f with respect to y is 3y squared. Partial of f with respect to z is 4z cubed. So the partial of f with respect to x at the point 1, 0, 1, when x is 1, this is 2. Partial of f with respect to y at 1, 0, 1, when y is 0, this is 0. Partial of f with respect to z at 1, 0, 1, when z is 1, this is 4. So the tangent plane has the equation 2 times x minus 1 plus 0 times y minus 0 plus 4 times z minus 1 equals 0, or 2x plus 4z minus 2 minus 4 minus 6 equals 0, or x plus 2z equal 3. So this is the equation of the tangent plane to the curve at this point. You'll notice 1, 0, 1 satisfies this equation, so this plane does go through our point, and that's the equation of the tangent plane. Any questions about that? So I said there are two forms for a level or a surface. It could be the graph of a function of 2 variables, or the level surface of a function of 3 variables. So I've just been looking at the case of a level surface of some function f of x, y, z equals 0. Suppose the alternative description, we have a function z equals f of x, y, and we're looking at the graph of this function. But I can rewrite this in this form. If I have z equals f of x, y, I'm looking at all the points that satisfy that equation. That's exactly the same as looking at the function capital F of x, y, z equals z minus f of x, y. And I'm looking at all the points where that is 0. Right? This equal to 0 is exactly the same as this. And if I write it in this form, what is the equation of the tangent plane? It's the partial of f with respect to x times x minus a plus partial of f with respect to y, y minus b, plus partial of f with respect to z, z minus c equals 0. This is for a point f of a, b equals c that lies on the plane. But the partial of f with respect to x is minus the partial of little f with respect to x. Partial of f with respect to y, with capital F, is minus the partial of little f with respect to y. And the partial of capital F with respect to z is 1. So I have this equation, which I can, and c is equal to f of a, b. So I can rewrite this as z equals this on the other side, partial of f with respect to x at ab times x minus a plus partial of f with respect to y at ab times y minus b plus f at ab. This is the equation of the tangent plane. And in this form, it should look very reminiscent of the equation of a tangent line, which is y equals f sub x of a, which is x prime of a, x minus a, plus f of a. So this is a complete analogy with this. Instead of f at a, it's f at ab. We have two derivatives with partial of f with respect to x and with respect to y. And this corresponds to exactly these two factors. So this is the equation for a tangent plane in its second form. So suppose we have the function z equals f of x, y, which is 32 minus 3x squared minus 4y squared. If I evaluate this at the point 2, 1, I get 32 minus 3 times 2 squared minus 4 times 1 squared. That's 32 minus 12 minus 4. 32 minus 12, this is 16. So the point 2, 1, 16 lies on the surface. So, and for this function, the partial of f with respect to x is minus 6x. Partial of f with respect to y is minus 8y. So the equation of the tangent plane is z equal to partial of f with respect to x at when x is equal, we're at the point x, y, z equal 2, 1, 16. That's the point on the, this is really ABC. That's the point on the surface. Minus 6 times 2. Sorry, 32. Oh, that's right. So for the tangent plane, z is equal to partial of f with respect to x evaluated at 2, 1, that's minus 12 times x minus 2. Partial of f with respect to y, minus 8y at 2, 1 is minus 8 times y minus 1, plus f of ab is plus 16. So this is minus 12x minus 8y. 24 plus 8 is 32 plus 48. Or I can divide by 4 and rearrange this slightly. I get 3x plus 2y equals 12. Oops, sorry. I can't do that. This is equal to z. So z equals minus 12x minus 8y plus 48. That is the equation of the tangent plane. And we can also use this to give a linear approximation to my function f of x, y at a point A, B. So here's the idea. Here's my surface. Here's the point A, B. And on that surface, going through the point A, B, I have a tangent plane. And so for x, y, close to AB, f of x, y is approximated by, on the tangent plane, f sub x at AB, x minus a, plus f sub y at AB, y minus b, plus f at AB. The value of the function here, plus a little bit in each direction. So what's an example of a linear approximation? So suppose I have, so this is an example. F of x, y is the function 5 over x squared plus y squared. So what does that look like? At the origin, it's infinite, right? But for example, on a circle of radius r, this looks like 5 over r squared. This is some kind of surface that looks like this. The bigger x squared plus y squared is, the smaller this function becomes. And suppose I want to, and on this surface, if I take f of, if I x equal minus 1, y equal 2, minus 1, 2 is 5 over 1 squared plus 2 squared. That's equal to 1. So sitting on this surface, there is a point minus 1, 2, 1. And I want to approximate the function by this plane, by this linear function. So the tangent plane will be the following. It is, or a linear approximation by looking at the tangent plane. It's f sub x at AB, x minus a, plus f sub y at AB, y minus b, plus f at AB. So this is going to be approximately equal to f of x, y. So I need to calculate this. For this function, the partial of f with respect to x is 5 x squared plus y squared to the minus 2 times 2x. So because this is 5 x squared plus y squared to the minus 1, so you get minus, so it's minus 2x minus 10x, 2 times 5 over x squared plus y squared to the 5th. And f sub y will be minus 10y over x squared plus y squared to the 5th. So at the point minus 1, 2, f sub x of minus 1, 2 is minus 10 times minus 1, that's 10. 1 squared plus 2 squared, that's 5. This is 5 to the 5th. Ooh. Sorry, squared. So this is 5 squared. So I get 10 over 25, or 2/5. The partial of f with respect to y at minus 1, 2 is minus 20 over 25, which is minus 4/5. And f at 1 minus 1, 2, we saw was 1. So the tangent plane is 2/5 x plus 1 minus 4/5 y minus 2 plus 1. Which is the same as 2/5 x minus 4/5 y, 2/5 plus 8/5 is 10/5 is 2 plus 1 plus 3. So this is my linear approximation. So this is approximately equal to 5 over x squared plus y squared for xy approximately or close to the point minus 1, 2. So this is really quite a beautiful and remarkable way to analyze functions, because this is rather complicated. This is much simpler because everything is just linear in x and y. And this is my linear approximation to the function. There is a kind of shorthand notation for part of this, which is the following. So if we have z equal f of xy, then the tangent plane is given by z equals f sub x at a point AB, x minus a, plus f sub y at AB, y minus b, plus f of AB. This expression is sometimes called dz. So, or what we often write, this is a small change from x to a and y to b. You sometimes write dz is f sub x at xy dx plus f sub y at a point xy dy. This is something called the differential, which for us is not particularly important, but it's useful to know what it is and to see it. Let's see if I can do one or two more problems, just because this is really quite interesting. Suppose I have the function z equal to the inverse tangent of xy, or the arctangent of xy, whichever notation you prefer. And if we take the point x equal y equal 1, z is the inverse tangent of 1 times 1, which is the inverse tangent of 1, which is pi over 4. As you know, if you have an angle of pi over 4, the tangent is 1. So for this function, let's find the tangent plane. So compute the tangent plane at the point 1, 1, pi over 4. So my function z, or f of xy, is the inverse tangent of xy. What's the derivative of the inverse tangent of x? It's 1 over 1 plus x squared. So the partial of this function with respect to x is 1 over 1 plus x squared y squared times the derivative of this with respect to x, which is y. And the partial of f with respect to y is 1 over 1 plus x squared y squared times the partial of xy with respect to y, which is x. So f sub x at 1, 1 is 1 over 2. F sub y at 1, 1 is 1 over 2. So the tangent plane has the equation just put it in the standard form. So the tangent plane would be in the form z equals partial of f with respect to x times x minus 1 plus partial of f with respect to y, y minus 1 plus the value of the function at 1, 1, which is pi over 4. So that is the equation of the tangent plane, or z equals a half x plus a half y minus 1 plus pi over 4. Or a half x plus a half y minus z equals 1 minus pi over 4. All of these are equivalent and they're all equal to the tangent plane. Suppose I have the function f of xy equals the square root of x squared plus y squared. So if x squared plus y squared equals r squared, f of xy is the square root of r squared, which is r. So if you're on the circle, x squared plus y squared equals r squared. That's the circle of radius r. The height of the function is r. So if you were to try to graph the surface, z equals the square root of x squared plus y squared, that's a cone. So the surface is a cone whose vertex is at the origin. Suppose I want to find a linear approximation at the point 3 minus 4. What is f of 3 minus 4? It's the square root of 3 squared plus minus 4 squared, which is the square root of 9 plus 16, or the square root of 25, or 5. So the point 3 minus 4, 5 lies on this plane. I want to estimate f of 3.06 minus 3.92. So this is a point close to 3, and this is a point close to minus 4. I want to find the linear approximation to the function and use it to calculate this. So if that's my function f of xy is x squared plus y squared to the 1/2 partial of f with respect to x is 1/2 x squared plus y squared to the minus a half times 2x. That's x over the square root of x squared plus y squared. And the partial of f with respect to y is 1/2 x squared plus y squared to the minus a half times 2y, which is y over the square root of x squared plus y squared. So the partial of f with respect to x at the point 3 minus 4 is 3/5. Partial of f with respect to y at 3 minus 4 is minus 4/5. So the tangent plane z is 3/5 x minus 3 minus 4/5 y plus 4 plus f at 3 minus 4 plus 5. So this is my approximation, my linear approximation to f. So if I so f at 3.06 comma minus 3.92, this is approximately 3/5 times x minus 3.06 minus 3, 0.06, minus 4/5 times y plus 4. If I add 4 to that, I get 0.8 plus 5. So this is 0.18 over 5 minus 0.32 over 5 plus 5. So that's 5 minus 0.16 over 5. What is that? 0.16 over 5 is 5 minus 0.032. So as you move from 3 negative 4 to 3.06 and minus 3.92, the change in the function from 5 is approximately 0.032. That's my calculation. Okay, well, no one ever said vector calculus was easy, but there really is a great deal in these sections to try to understand and to try to think about. And I strongly encourage you to work on problems. And if you get stuck, as invariably everyone does, to come to a problem session and ask me to show you how to solve a problem. But this is the sort of thing which will definitely be on the exam next week. You have to know how to find the tangent plane to a function and how to find the linear approximation to a function of two variables. Any questions about this? Otherwise, we will be done for the morning. And I will spend all day Wednesday going over problems on the review sheet. But I might not be able to cover them all, so it's helpful if there's a problem you particularly want me to try to solve, to ask me at the beginning of the hour. Okay. All right, if that's it, we'll be back on Wednesday. Bye, everyone.